Now let me show you how two-way ANOVA works. Okay, so if you have more than one grouping factors. Before we had only one grouping factor, it's a tree or fertilization protocol. Now let's assume that we picked up our sample in 2 different days. Some apples were picked up in a rainy day, and then some apples in a sunny day. Okay, so let's see if we can actually use ANOVA to see the difference between days and to see the difference between trees simultaneously. Okay, so let me give you some numbers. Again, I will use very simplified numbers, not the real ones, just to make the calculations easier. But it doesn't matter, because when you start working with real numbers, the calculations will be actually the same. Let's say that first you picked up 3 apples in a rainy day, and this was the sugar content in these apples, 9, 10, 11, and 11, let's say 10, 11, and 12. So this was rainy day, okay. And then, for example, in a sunny day, we got 3 apples, 12, 13, and 14 for this case. Then we have 13, 14, and 15 in this case, and then 14, 15, and 16 for this case. Okay, so let's assume that was the sample. Okay, now let's calculate this. This is sunny day. Okay, so let's calculate the average value. So you can see that, for example, for rainy days, the averages are 9, 10, and 11. For sunny days, it's 13, 14, 15. So the average, we can just take average of these two. Okay, so we have 11 here, we have 12 here, and we have 13 here. So these are average values, and apparently that the grand average will be 12. So we have the same grand average as in the examples before. Okay, now we do the transformation, so we have to subtract the average value first. So these are our new values, A, B, and C. So if you take 8, subtract the average will be -4. Then you have -3 and -2 here, right? Then you have -3, -2, and -1. And then it's -2, -1, and 0. So these are the centered values for the rainy day. And now we have to do the same for the sunny days, right? So it will be 0, 1, 2. It will be 1, 2, 3. It will be 2, 3, and 4. Okay, so these are centered values. And again, if you look at the average values, so you can find out that this is -1, this is -1, and this will be 0, and this will be 1. So the effect between the trees is the same. Okay, it's more or less the same. Now let's calculate the systematic variation. So systematic variation. And look, now we have 2 sources of systematic variation, right? So it means that we have systematic variation because we have different trees, and we have systematic variation because we have 2 different days or 2 different weather conditions. So we will have 2 matrices. And the idea is the same. Let's start with the trees. If we live in an ideal world without any random factors, every tree will have the same amount of sugar in, right? Every apple from each tree will have the same amount of sugar. So we have 0, -1, -1, -1 here, and then I'll just make it like this, -1 and -1. And then you have 0, 0, 0, 0, 0, 0, and then you have 1, 1, 1, 1, 1, 1. So this is a systematic variation for the part connected to the trees, right? So this is the trees. Now we have another one, A, B, C, for this. So I will just write the trees here. And this is weather, and this is weather, right? Now think a little. How we can calculate the systematic variation for the weather? Well, apparently all these values were taken from the rainy day, right? And then all these values, it's for sunny day, okay? Let's assume the same. If we don't have any random factors, in the rainy day, we should have the same values. In the sunny day, we should have the same values, right? So we need to calculate the average for these two. We need to calculate the average of these two. Then let's just calculate it. So we have 9 in the top. Then we have 6 in the second row. We have 9 here. We have 6 here. Then we have 3 here. It's minus, of course. -3, -6, -9. So together it's -18. And then you can see that you have 9 values, right? 9 values. So -18 divided to 9, it's -2. So it means that it should be -2, -2, -2, -2, -2, -2, -2, -2, -2. Meaning, if you pick up apples in a rainy day, the amount of sugar should be by 2% of total mass smaller than the average. Okay. And then if we do the same here, so we will get positive values. Okay. So it means that the average is 18. the average is plus 2, the total sum is 18. And then we'll just write it 2, 2, 2 here, 2, 2, 2, 2, 2, 2. Again, it means that if we pick up apples in a sunny day, then the sugar amount in this apple should be by 2% larger than the average, right? And then we have, of course, the residual variation, ABC. So the same idea, you take like -4, -1, -2, and then we have minus in between, so it will be -4 plus 3, so it will be -1 here. Then you have -3, -1, -2, so it will be 0 here and 1 here. And then if you continue, you can see that it's the same. Okay. And then for the second case, we have 0, -1, it will be 1, and then -2, it will be -1. We have 1, -1, it will be 2, and then -2, it will be 0. So if you continue calculating it, you will get the same values here. Okay, so this is our residual variation. Again, it doesn't look random. In reality, residuals are always random because you got rid of all systematic sources of all systematic variation. But in our case, of course, it doesn't look random because we have this trivial simple numbers. Okay. Now we can do the same calculations as before. So first of all, let's calculate the sum of squared values. And here we have 12 ones and 6 ones, 6 minus ones, and then 0. So it will be 12, right? So it will be 12 here. Now here we have -2s and 2s. If you take 2 or -2 in the power of 2, it will be 4. And then we have 18 by 4, which gives us 72. Okay. Now here it's easy. We have -1s and 1s. If we square them, it's the same. It's 1. Then we have 1, 2, 3, 4 times 3. We have 12. So this is a sum of squared values. We just square every value and take a sum. Okay. Now the degrees of freedom. Let's think. At the beginning, we had degrees of freedom equal to 18. That's the amount of values we had, right? Then we lost 1 degree of freedom when we calculate average and subtract the average, right? Here we have 3 groups. How many degrees of freedom we need to compare them? We need 2, so we lost 2. Then we have 2 groups here. How many degrees of freedom we need to compare? It's 1. So we have 14 degrees of freedom which is left. Okay. Now we can take the ratio between the sum of squared values and degrees of freedom and calculate the variances. So the variance, the systematic variance for the trees, will be 12 over 2, which gives us 6. Okay. Then the systematic variance for the weather will be 72 over 1, which is 72. And then the systematic variance, the residual variance, is 12 over 14, which is approximately 0.86. Okay. Now we can calculate F values. The F value for the tree, for the difference between trees, is 6 over 0.86. And the F value for the weather, it will be 72 over 0.86, right? The first F value is approximately 7 if we round it, and the second is approximately 84 if we round it again. Okay. Now, how to find the p-value, the corresponding p-value? The same values as we did before, right? Let's take the trees first. So the trees, the p-value for the trees will be 1 minus the CDF, so PF in the R, then 7. How many degrees of freedom for systematic variation? It's 2. How many degrees of freedom for random variation? It's 14. Okay. Yes. And then for the weather, it will be the CDF. We have 84 as a F value. Then how many degrees of freedom for systematic? It's 1. For random, it's 14. Okay. Then if we use R to calculate the p-values, the first will be 0.08, which is less than 1% again. It's very extreme, right? So we see a difference here. It's very small chance that we can get these values by randomly, by chance, right? And in this case, it's even more extreme. It will be 0.1, 2, 3, 4, 5, 6, and then 27. Okay, so it's very small value. Here we definitely have a very clear evidence for the difference. Okay. So the two-way ANOVA, we try to split the all variance into systematic parts and then every factor has its own systematic part, right? And we eliminate them. So one systematic part does not influence the other systematic part. And then the residual variance. Then we calculate F value for each of the factor, and then we use the F distribution to calculate a p-value to see how extreme our sample is from being taken from populations where there is no difference between trees, then there is no difference between days. Okay, it's very important to use all systematic factors you have, because if we, for example, do one-way ANOVA and forget that we have different weather conditions, we will not see the difference, because this variance will be in the random part. If we don't eliminate it from the random part, this will be, all these two values will be together. So the random variation will be huge in this case, and we will not be able to see a difference between the trees. But because we did it correctly, so we took weather as an additional factor, ANOVA was able to distinguish the differences. And now we can clearly see the difference from each of the factors. Okay. The only problem here is that, yeah, we see a difference, but how big the difference is? Let's discuss it in the next block.